Hello there, ATS EVS 105 students. Dr. John Schrage here, and today we're going to be continuing our discussion about the carbon cycle by talking about the ways in which humans are modifying it through our activity. Remember, our adjective that we like to use for modified by human activity is anthropogenic. Humans gave rise to. And so these are going to be modifications or components of the carbon cycle that are due to human activity. Now, all these results that I'm going to be showing you here are authoritative in the sense of what you just saw in the little introduction here. They are authoritative in the sense that they have been vetted by the scientific process and confirmed by experiment and so on. We'll be learning more, of course, over the course of the semester about how that scientific process works and so on, but these are results confirmed by experts as we've been learning throughout the semester. Now, what I'm doing here is I'm just reproducing one of the figures we saw when we talked about the natural aspects of the carbon cycle. Here in each of those hexagons there, I've put one of the reservoirs of carbon in the Earth atmosphere or ocean system, like the land biosphere or the deep ocean and so on. And then, of course, off to the side, I have the very large reservoir that is rock, or the lithosphere, to use the right word. And then with the arrows there, I'm showing in units of gigatons per year the transfers in the natural carbon cycle between the different components of the carbon cycle and how they all kind of balance on geologic timescales. Well, if we're going to be talking about ways in which humans are perturbing or upsetting the natural carbon cycle, clearly the first one we want to talk about is going to be the burning of fossil fuels, which is a way of directly transferring carbon from rock into the atmosphere. By combustion, we are converting carbon that is stored in the lithosphere, in rock, into a gas that's in the atmosphere. Let's just real quick here make sure we're all clear on this idea of fossil fuels. Fossil fuels form when plants that grew hundreds of millions of years ago are buried before they get a chance to completely decay. And that, because if they were decaying, bacteria and fungi and things like that would be returning that carbon dioxide, that carbon, back to the atmosphere through their processes of respiration. These fossil fuels are these organic materials from these decomposing plants are then buried under high pressure and heat and are converted over the period of millions of years into fossil fuels like petroleum and coal and natural gas and so on. Then we find them useful and dig them up or extract them or whatever, and we burn them as a way of getting energy for the modern world. Chemically, this act of burning fossil fuels turns out to basically be the same chemical reaction as respiration. The fuel, be that gasoline or diesel or natural gas or coal or whatever, is combined with oxygen to produce carbon dioxide, water vapor, and energy, very much like the respiration process does with natural carbohydrates like sugars and starches and so on. So when you look at like a coal-fired power plant, like what we're seeing in this picture here, you can get a sense that there are emissions coming from this plant. Now, that's actually a little trickier than you might think. It's easy to look at this and find it very disturbing because you're saying, oh my goodness, look at all this stuff coming out here. Look at all the smoke coming out of the smokestack. That's actually not what's going on here. Most coal, pretty much all power plants are clean enough. You're not seeing any smoke here. Most of that white stuff that you see coming out of the smokestacks there is actually cloud. It is water vapor that has condensed into little liquid water droplets in much the same way that happens like in a cloud or fog or something like that. So like these plumes that you're seeing here, that's not smoke. Nor is the lower one here. Now in the case of the lower one in this particular picture, it's instructive to see that that's actually just a cooling tower. Part of the efficient operation of a power plant is you have to have a cooling tower to cool one part of the process that generates electricity. The cooling tower there uses water, fresh water, to cool the plant, produces steam, and then it vents that out and eventually condenses out into these clouds. Just north of the old gym on Creighton's campus, there's an electrical power, there's a cooling station. I'm not quite sure what they do there, but it's giving off kind of a cloud on like any given cold day. That's not, I mean, yes, water vapor is a greenhouse gas, but it has a very short lifetime in the atmosphere and so on before it falls out as precipitation. That's not really the concern here. Now, this taller plume coming off this smokestack, that is actually exhaust coming from the combustion of the coal. And that plume is full of carbon dioxide, but you can't see it because carbon dioxide is colorless and odorless and invisible as gases go. What you're seeing there is, again, water vapor that is condensed. You can't see water vapor. It's colorless and odorless and so on too, but it's quickly condensing into drops of cold water as it comes out of that hot smokestack and into the colder atmosphere around it. You're effectively seeing a cloud that's being made by the combustion of the fuel. The same thing is true of like when you see a car exhaust on a cold day. On a cold day, when you see what looks like smoke or something coming out of the back of a car's tailpipe there, what you're seeing is coming out is a mix of carbon dioxide and water vapor. Now, on a cold day, the water vapor, as it mixes with the colder air around the car, forms a little cloud. But, I mean, the water vapor is not so much the issue there. It's all the carbon dioxide that's coming out of that tailpipe that's the greenhouse gas that we're worried about. All of these fossil fuels that are buried down deep in the earth are part of the natural carbon cycle. And given billions of years, all of that fossil fuel would have eventually cycled through the carbon cycle and been recycled back up into the atmosphere by volcanoes or something like that. All these layers of coal, though, that would take billions of years for that part of the continental plate to subduct someplace and then be recycled through the mantle of the earth up into the magma chamber of a volcano and all the kinds of things like that that you loved learning about in, like, you know, 7th grade earth science or something like that. It would have happened, but on enormous life. I mean, it's not, the solar system isn't old enough for that to have happened yet. Okay, it would take a very, very long time for these deposits of fossil fuels to recycle in that way. In contrast, of course, we dig them up and bring them into the atmosphere at an enormous rate. At the present time, the burning of fossil fuels is bringing carbon from the rock into the atmosphere at a rate of about 9 gigatons a year. 9 billion tons of carbon atoms per year. That is about 90 times the natural rate at which carbon is transferred from rock into the Earth's atmosphere. This is a huge perturbation to the overall carbon cycle of the Earth. And we do it because we love fossil fuels. They make the modern world work. We need a train a mile long of coal. Those train tracks in Omaha that run parallel to I-80 bring coal from Wyoming eastward. Those trains are about a mile long, and they come by about every 5 minutes, 24 hours a day. That is an enormous amount of coal, and that is one train line that is bringing that coal eastward. There's lots of other ways in which we're moving, and coal is only one fossil fuel. There's also petroleum, which we pump out of the ground at millions of locations all around the world, not just in Texas and not just in Saudi Arabia and places like that. And then we haul it in enormous supertankers all around the planet. We are extracting all this carbon, all the methane that is being pumped out of shale around the country and so on, all the fracking and so on, results in enormous contributions to the carbon cycle by humans. This little graph here only goes as far as 2000, and so at that time our total fossil carbon emissions were around, what would that be, about 6.5 gigatons per year. But if we extended it to the present time, it's right around 9 gigatons per year. I think your book is using the number 8.6 gigatons per year. An enormous transfer of carbon from the lithosphere into the atmosphere. Another difficult anthropogenic way in which we are disturbing the carbon cycle is through deforestation. Deforestation transfers another 1.5 to 2 gigatons of carbon, this time from the land biosphere, into the Earth's atmosphere. And it's not so hard to see how that happens when you look at deforestation. It's pretty horrible stuff. There's an enormous amount of carbon that is being stored in the form of trees. Both their trunks and their leaves and their roots below the ground and so on. Every acre of the forest has several dozen tons of carbon. And when you cut that down, even if you use that wood for something useful versus, say, burning it, sooner or later the carbon in that wood will end up back in the atmosphere by decomposing or being burnt or whatever. But it will be transferred back up into the atmosphere. That is carbon that used to be in the land biosphere that is now where it couldn't hurt anybody, where now that carbon has been transferred up in the atmosphere where it's part of the greenhouse effect. you don't have to just burn the wood for this to work either. I mean, for example, it's often the case that there's not any economically useful wood in the rainforest that is being taken down, and they just bulldoze it and bury the stuff. But the trees that they bury and so on, that all decomposes and works its way through the biosphere, and then eventually by respiration back up into the atmosphere as it decomposes too. Right off the bat, when you first just knock the forest down, you are clearing it. About 30 to 60% of the carbon that was there in the form of the tree trunks and so on is in the atmosphere almost immediately by burning or by consuming the forest products and so on. Whatever's unburned or unconsumed will decay and be into the atmosphere within, on average, lifetime of about 10 years. So deforestation is a pretty fast and robust way to transfer carbon from the Earth's biosphere up into the atmosphere. Now, admittedly, 1.5 to 2 gigatons is a lot smaller than the natural respiration, which you can still see on that diagram under those arrows there, is about 100 gigatons per year. But this is an imbalance. The 100 gigatons that is being sent from the land biosphere into the atmosphere by respiration is perfectly balanced by the 100 gigatons that's being transferred each year by photosynthesis. This is an imbalance. This is a net transport of carbon from the land biosphere into the atmosphere. It's surprisingly hard to get a handle on how much deforestation is actually happening. Obviously, a lot is already in the past. This is why, by the way, things like carbon dioxide concentrations in the Earth's atmosphere started going up well before the Industrial Revolution, because we were already pretty good at deforestation, even before we started digging coal and petroleum and so on. I mean, almost all of the United States was covered with forests before we decided to start cutting them down and raising corn and grazing cattle and so on. Not to mention Europe and other parts of the world that were also forested, and, well before the Industrial Revolution, all those forests were lost. But even in our times, like this diagram here, which I believe comes from the World Wildlife Federation, had a map, and the red areas in the Amazon on this map are places that have already been deforested. This is a hard thing to get a handle on as to the exact measurements, because it isn't like every single tree that's in those red areas is gone, and it's not like every single tree that's in the green areas is still there. It's kind of more nuanced than that. But it gives you an idea. There's still a lot of forest in the rainforest, but we're cutting it down fast. And every one of those acres is precious. Every one of those acres of the Amazon rainforest contains about 50 to 100 tons of carbon that we don't really want up in the atmosphere. It's doing good down here on the ground. We want it to stay down there. And that's why forests are so good, because the carbon that goes into the forest stays in the forest. There's a net storage of carbon in the forest. Let me use Brazil as an example. Brazil, most of the deforestation that happens in Brazil is to raise, of all things, soybeans. Someone owns land by one mechanism or another, they deforest it, and then they plant soybeans there. Soybeans are good. We need soybeans in the world. I'm not sure we need soybeans where there used to be a forest. This actual picture right here that I'm showing you right now, that used to be rainforest. Now it is a soybean field. It used to look like Brazil, because it is Brazil. It now looks like Nebraska. Okay? And this acre right there that you're seeing, I mean that's more than an acre, but whatever, stores virtually no carbon. The soybean plants grow during the summer. They take carbon dioxide out of the atmosphere and use sunlight and carbon dioxide to make food for themselves, but then at the end of the season they die, and by respiration the bacteria and so on that consume the plants send it all back to the atmosphere. There's nearly no net storage. Yes, there's some net storage in the microenvironments of the topsoil and stuff like that, but for all intents and purposes this is a carbon neutral environment now. Okay, instead of storing carbon neutral is a bad choice of words there. Instead of storing large amounts of carbon, there's no net storage here in the soybean field. The same as would have been true if I'd shown you pasture or a date palm farm, which is often what deforestation is used for in the tropics. Deforestation and the burning of fossil fuels certainly get the most ink in terms of ways in which humans are affecting the carbon cycle. But there's actually two more components here that I've labeled just as enhanced. You have a version of this diagram in your textbook that's maybe a little less PowerPoint, a little more technical looking. let's actually look at the first one here, the one that's farther to the left on this diagram here, that shows carbon being transferred from the atmosphere into the land biosphere. Human activity does actually enhance the transport of carbon dioxide from the atmosphere into the land biosphere, whereas the natural carbon cycle is about 100 gigatons per year being transferred from the atmosphere to the land biosphere by the process of photosynthesis. Actually, human activity does enhance that. When you enrich the atmosphere with more carbon dioxide, all else being equal, plants like that. Plants do thrive in an environment with more carbon dioxide, as long as everything else is equal, and it's also much warmer, and it isn't raining because you're experiencing a drought. All else being equal, adding carbon dioxide does make plants do better. That's where these crazy anti-regulation of petroleum type websites like Plants Need CO2 and Carbon Dioxide is Green.org and things like that get their ideas. I mean, it is true. Under laboratory conditions or in a greenhouse, if you artificially elevate the carbon dioxide concentrations without changing anything else, plants do better. And the same is true out there in the natural world. When the carbon dioxide concentration is higher, it is true. There is more photosynthesis in corn and in soybeans and in rice and so on. But this is not, and that is a net transport of carbon out of the atmosphere towards the land biosphere. It sounds like it's helping our problem, and it is helping. But keep in mind that this enhancement of the carbon dioxide concentration is affecting all the plants. Not just like forests, which will hold that carbon for centuries, but things that grow just in one growing season, like crops, corn and soybeans and rice, where yes, the corn is having slightly more photosynthesis and growing slightly more and producing more corn, slightly because of the increase in the carbon dioxide that it's extracting from the atmosphere by photosynthesis, but that'll all just return to the atmosphere when bacteria decompose the corn plant at after the growing season. It's only that small part of this that is more permanently stored in forests, which, let's be clear, we're not that great about keeping around anyway, right? Even if these trees are slightly healthier because they are in an environment with an enriched carbon dioxide atmosphere, which is not so great anyway, but more importantly, we're probably going to cut them down. That tends to be what we do. So it's nice that there's some carbon going from the atmosphere into the land biosphere, but it's not a solution. It is not, we are not enhancing that flow of carbon from the atmosphere to the land biosphere by anywhere near enough to offset the burning of fossil fuels, and frankly, we're not that great as to how much we're keeping in the land biosphere anyway. Similarly, there's this right arrow over here that labeled enhance, which is showing a transport of carbon from the Earth's atmosphere into the mixed layer of the ocean, the top 700 meters or whatever. Yeah, absolutely. The way carbon gets from the atmosphere into the ocean is by being in contact with the surface of the ocean and mixing in and dissolving into the ocean. This is why the ocean was storing more carbon dioxide when we were talking about the natural carbon cycle. So you elevate the amount of carbon dioxide in the atmosphere, you increase the rate at which carbon dioxide is transported into the ocean by dissolving and forming carbonic acid. But wait, that's a bad thing, right? We don't like the ocean acidification aspects of this. It was harmful to creatures that lived in the ocean. Earth's oceans were more acidic than they've been any time in the last 20 million years, according to paleoproxies. That's not a good thing. I mean, yes, it's getting some greenhouse gases out of the Earth's atmosphere, but all it's doing is taking one problem and making a different problem out of it. Okay, this is not solving our climate problem either. And so if we take a look and put all those arrows on the same diagram, and again, you have a more professional looking version of this diagram in your textbook, what you get is the complete carbon cycle, including any modifications that we are seeing due to human activity. How well do we know this stuff? I mean, if I wanted to put some numbers on here, like I have got, like 9 gigatons of carbon per year being burned by fossil fuels, how well do we know that? Well, in the case of that number about fossil fuels, we know that number really, really well. See, we have all those fossil fuels are being extracted from the ground by big companies who keep track of what they extract. They report it to shareholders. They might have to report it to various federal agencies and so on. We know to high precision how much carbon we're pulling out of the ground each year in the form of coal, natural gas, petroleum, etc. And it isn't like we store it, okay? BP is not in the business of like pumping oil and then just leaving it in tanks, for a rainy day. Or some coal company isn't in the business of digging up coal and then just putting it in a shed because someday we might want it. No, if they pulled it out of the ground, they sell it and it gets burned. Nobody keeps fuel around the house just in case someday they need to fill up their tank, right? If we pull it out of the ground, within a relatively short period of time, we burn it. So we actually know that number really well from like stock filings and financial reports of petroleum companies and things like that. Similarly, this number that is the total amount of carbon that's stored in the atmosphere, we actually know that really well too because that's just an observation. We can just use in situ observations of the amount of carbon dioxide at the present time to determine, okay, if we just took this sample of air and we found this much carbon, then multiplied across all the air in the atmosphere, we have this much carbon. We actually know that number, again, to lots of decimal places. We've got that number under control. And in fact, we could make a graph like this one that comes from your textbook, where that bottom curve that kind of looks like a sawtooth curve, that is the observed amount of carbon dioxide in the Earth's atmosphere. Remember, it has that little sawtooth pattern to it because of the annual cycle of carbon dioxide in the natural environment. And then on this graph, what they did is they put that dashed curve there. And that little dashed curve is saying, if all the fossil fuels that we had burned, if all that carbon dioxide had just gone in the atmosphere and stayed there, I mean, we know how much fossil fuel we've burned. In this case, it's since 1959. We know how much fossil fuel we have burned. What if that was all just still up there in the atmosphere? There weren't any transport of carbon out of the Earth's atmosphere by enhancement of the land biosphere or enhancement of the transport into the Earth's oceans. So we have two different curves here. What we should, that dotted line, let's say should, what we should have in the Earth's atmosphere right now, if based on all the stuff we've burned, coal, natural gas, etc., and the sawtooth line is what we really have in the Earth's atmosphere. And what you see is that there's a fairly big difference between the two curves. Now keep in mind, this is another one of those kind of curves where the y-axis on the graph here doesn't go all the way down to 0. I mean, so the difference is smaller than it looks on this particular graph, but it's still a pretty big difference between those two curves, and the difference is about the uptake of carbon from the atmosphere into either the land biosphere or the ocean. The land biosphere is extracting carbon dioxide from the Earth's atmosphere, by enhancing photosynthesis and things like forests and so on. And the ocean is extracting carbon dioxide from the Earth's atmosphere, but as the amount of carbon dioxide in the atmosphere goes up, there's more carbon dioxide dissolved into the ocean. That's why the ocean is acidifying, as we talked about in the last lecture. Boy, once you start looking at this graph, you realize the land biosphere and the ocean, they're doing us a huge favor here. At the present time, the Earth has this diagram only goes to about 2008 or 2010 roughly. At the present time, the Earth's atmosphere has about 400 parts per million of carbon dioxide, but you can see if we extend that curve up there, present concentrations would be around 440, 450 maybe, if it weren't for the land biosphere and the Earth's oceans taking some of that carbon back out of the atmosphere. The planet would be warming even faster and even more if it weren't for this uptake of carbon dioxide by the biosphere or by the oceans. In fact, that's the area that between those two curves. And if I highlight it there, that is the amount of carbon that is apparently being extracted by the atmosphere by the two processes I highlighted there in blue. Oh, okay. Yay biosphere, yay oceans, you're keeping this from being such a big problem, right? Okay, good, except, can it happen forever? Is this going to just continue into the future? Will the atmosphere always be able to transfer more carbon into the ocean in the form of, carbon dioxide that dissolves into seawater? Or will there be some point where the seawater is, shall we say, saturated with carbon dioxide and no more can dissolve into it? That would be bad, because we're kind of counting on the ocean helping us here and extracting some of that carbon dioxide. Same with like the land biosphere. At the present time, we apparently are able to get plant material in long-term storage like forests and so on. They are doing more photosynthesis. Forests are bringing more carbon dioxide out of the Earth's atmosphere and storing it in the form of wood and roots and things like that. But can they keep doing that? Or is there some limit, like where the forest just can't take up any more carbon dioxide per acre? That would be very, very bad if that was the case. Let's just then kind of do a little thought experiment here. Let's say at the, I have that red line drawn there, and if you go down to the x-axis, it's about 2005. Let's say that the difference between the amount of carbon dioxide we were burning, releasing from fossil fuels, was a certain difference from what was actually being observed. The difference being how much the carbon dioxide the environment was able to pick up in the form of the land biosphere and the oceans. What if that was all it could do? What if from there on out, if we just extended those curves forward into the future, the oceans or the land biosphere just can't pick up any more carbon dioxide? Well, then from there on out, the distance between those curves can't change. From there on out, whatever we burn into the Earth's atmosphere, that's it. We got to have that much in the atmosphere. So from there on up, notice that the slope of the line, what was that sawtooth line, the observed amount of carbon dioxide in the atmosphere? Look how the slope gets a whole lot bigger. The rate at which carbon dioxide gets added to the Earth's atmosphere starts going up. Uh-oh. So if the oceans at some point can't hold any more carbon dioxide, or if the biosphere can no longer pick up any more carbon dioxide, we have a serious problem. And that is an ongoing topic of research in this climate sciences. All right. We have one more little lecture to go about methane. But before we do, and move on to that, I do want to ask you a couple questions about what we just saw about the way the humans are affecting the carbon cycle. Question 1. Which of the following anthropogenic processes adds the most carbon to the atmosphere each year? Is it A, deforestation, B, respiration by animals, bacteria, etc., C, burning fossil fuels, or D, nuclear power? All right, look over those 4 options and click on one of them and get some feedback before you move on to question 2.